Good morning or good afternoon to everyone, and thanks for joining today's webinar. I'm Michele Merelli, part of Particleworks team based in Italy, and we promote particle simulation all around Europe and the world. So today we are here discussing Particleworks, this new simulation tool that allows to investigate new industrial, let's say, applications, and we will see validations, proven validation, test benches, validation in different sectors. So briefly going through the agenda of today. So here is an overview of the validation, the boxed one, the violet boxed one are gonna be discussed in detail. But I mean, in the table you see that there is a wider list, and I will provide you further documents if you like. So the idea of today's webinar will be first to introduce the method, Particleworks and moving particle simulation, and why it's key to improve product, especially in an increasingly digitized world. And then after, again, a fast, let's say, comparison between Particleworks, that is a meshless CFD tool, and the conventional CFD tool, so mesh-based CFD tool, we will go through the validations that are in the fields of transmission design, e-motor, electric motors, food and beverage, plastic recycling, and more. Okay, so as mentioned, here we see in the highlighted boxes the example we will look at, but I'm available at the end of the presentation to further discuss if you're interested in other sector like piston cooling or hydro turbines. So let's introduce the method and this simulation tool. So as we know, especially after the COVID pandemic, or in general, given the digitalization trends we see, we need simulation earlier in the design phase, because in this way we can do better design, we can iterate faster, and we can improve also the time to market and reduce the cost of the development. Simulation traditionally was mesh-based, was very complex, required, let's say, simulation engineer specialized in that. With Particleworks, we have a meshless approach that is easier to use, and in the next slide, we will see the key features and the differences between, again, traditional mesh-based CFD and this meshless approach. I just want to give you an overview of what type of physics are, or like, let's say, solvers are integrated in the software. We have moving particle simulation for liquid flow, but we can also analyze air flow with a finite volume method integrated inside the same interface. We have the possibility to integrate also powders or solid materials with a discrete element method solver. And we can also predict temperature in the solids with a conjugated transfer method. And we will highlight these kind of modules later on in the presentation. So as mentioned, what are the differences, the key differences here? Conventional CFD requires a mesh, so requires a user to, starting from the CAD, prepare the CAD, maybe clean up the CAD, remove some features that could not be easily meshed, and it requires a lot of pre-processing time. With moving particle simulation, basically the computational nodes that were conventionally this type of grid are actually the particle themselves. So at the beginning of the simulation, the software automatically creates this Lagrangian dynamic mesh, computational mesh, that is basically where we solve the computational fluid dynamics equations. Okay, so it's a meshless approach, is automatically computed and handled by the software. So because of that, the pre-processing is in the range of hours instead of weeks. And also hardware time can be further reduced because we can use the parallelization that this method allows, and we can run on graphic cards, and we can take advantage of graphic cards. And I can also discuss how the scaling of simulation times compare with conventional, let's say, CPU cores, so conventional computational nodes that might be more familiar with mesh-based CFD. So overall, we see that the workflow for a simulation with Particleworks is in the range of days instead of weeks. It's easier to set up, faster, and because of that, we can do it earlier in the design phase. So we can iterate on the geometry, we can check different conditions in the digital model. Here is a quick summary of the feature I mentioned. So you can work directly with the CAD. You don't have to be a simulation expert, and you can run on graphic cards, NVIDIA graphic cards. We all know how this sector is scaling and the improvements we see there thanks to AI, and we can benefit from that. And basically we can run, instead of on a cluster, on a very compact workstation, even laptop now, with very good performances. And here again is a quick summary of the workflow that is not needed. So we don't need this type of mesh generation with Particleworks, and we can speed up the workflow. So let's, of course, discuss validations, because every time we introduce a new method or a new workflow, we have to validate it. And I will show you some of the validation we already collected with our customers, presented at our conference, for instance. I will start with the transmission, that is the sector and lubrication. So we have this kind of flow prediction of splashing of oil in gearboxes and lubrication of gears or bearings. And this is one of the sector where Particleworks was first introduced. And this year at our conference in Frankfurt, we discussed and we heard about one very interesting validation compared to test bench. So basically, Punch Powertrain and Alberto Arcos showed how they could predict oil flow inside a gearbox, a complex gearbox. You can see how many rotating elements we have here. And with traditional CFD, this kind of system is, let's say, impossible to handle. But with Particleworks, they were able to run a simulation, compare it with the testing. So in general, in this sector, they have clear casing testing, and they could see, let's say, distribution of oil in certain areas. Here you see that there is a distributing pocket that is empty. So basically it's a collection, an area where oil can be collected and redistributed to the bearings, for instance. And you can see that in the initial design, we don't have any oil there. And the objective was, again, in the design phase, to change some geometrical feature in order to improve the splashing in that area. So you see here the improved version. They changed one geometrical element. I will show you the detail in the next slide. And thanks to that, they could achieve higher amount of oil in the upper region. It was also validated with the clear casing. And this is the simulation as compared to the data point from experiment. The amount of oil collected in that pocket was confirmed. And because the meshless approach allows for faster iteration, they could improve the design of this baffle that redirect oil more efficiently. Okay, so they tested 4 different design in 1 week, and they could achieve better distribution and lower temperature at the bearings. As mentioned, Particleworks integrates also a thermal model for temperature prediction. So if we want to push our simulation farther in complexity, we can not just simulate the oil, but also the temperature in the solid. For instance, in this transmission from Carraro, another partner that discussed at our conference last year, not this year, the approach. So basically they had this kind of 3-gear reducer transfer box for a wheel loader, a compact wheel loader. So they could both do the computational fluid dynamics, but also, as mentioned, the thermal model. The objective was to compare the temperature prediction at different bearings. So they have 6, let's say, sets of bearings here, and they wanted to see the temperature distribution at different operating points, so different rotational speeds, as compared to other simulation tools like ANSYS mechanical and also experimental data. So they also had thermocouples placed at the bearing sector, and we will see them. And they wanted to compare the full workflow of Particleworks temperature prediction with respect to the simulation. So here we see the 4 configuration analyzed. So we have two RPM condition, so 8,000 and 9,600 RPM, and 2 different rotational directions. So first thing first, in the design, they want to see how oil distributes, if oil enters, for instance, the bearings or not. You can see oil there, maybe more on the left than on the right, for instance, already visually. This is an output already very of interest. And then at the end of the simulation, what we can do is to map. So let's say extract heat transfer coefficient maps on the housing or on the bearings, and transfer those maps, HTC, heat transfer coefficient maps, to the thermal solver. The thermal solver, as mentioned, can also be inside Particleworks, is this module here. And what you see here is the final table. I just have to be very short in the discussion, but we can go in the details if needed. But you see the delta temperature between the thermocouples placed experimentally and the temperature prediction from the model. So what you see here now is not the HTC, but it's really the temperature distribution inside the gearbox and also in the bearings. So you see that the gaps are below 9 degrees all in all, and that was, let's say, the desired range for the application. Mean gap was 5 degrees, so very good accuracy between the full workflow in Particleworks and the thermocouples. Similarly, we did something in the e-motor cooling sector. We have new designs for the automotive electric motors that require oil jets, direct oil cooling, instead of like indirect water jacket cooling, because here we are looking at e-motors that are much more dense in terms of power densities. So because of the automotive sector requirements as compared to other electric motors for industry, for instance, we have to put more energy in less space, and also decrease, of course, the weights. So in order to achieve that, we have to also better cool. And as mentioned, traditionally, we could use air, we could use water flowing in this area, but now we see more and more designs where oil is injected directly in the most critical areas, like the coils here that are the region that heats up the most, okay? And one of the first validation of the method in this sector was performed with Ricardo in 2020 at our conference. And basically, you see here the full workflow of simulation for electric motors. So what is usually done is to first analyze the flow distribution inside the cooling channel. So here you see the part of the cooling circuit before it's, let's say, splashed towards the windings. So this is the rotor of the e-motor at the center. So one thing to do is to analyze how the rotating rotor can, the velocity of the rotating rotor can impact the flow distribution in different sectors. And then we can also do the air simulation inside the e-motor, because of course, as mentioned, basically in the area here between the rotor and the windings, we have air, and because of the rotation of the rotor, we can have some windage effect and cooling effect also for air. And then at the end, we want to analyze how oil distributes and also cools the most critical areas. Here you see an example of the heat transfer coefficient map on the windings. You see the jet impinging regions with very high heat transfer coefficient as expected. So you have to imagine that here we have two sets of nozzles that spray towards the windings. And what was done then was to transfer this kind of map information, HTC map, to a thermal model in order to predict temperatures and hotspots that could really lower the lifetime of the e-motor, like for instance, the magnets that are very sensible to temperature inside the rotor itself. And of course, as mentioned, we want to understand if there is a good correlation between simulation and an experiment. And Ricardo had 6 thermocouples on the windings, so in different location of the coils here of the windings. So you have to imagine, like in 6 location, they could see the temperature distribution. And you see here the gaps are below 5 degrees. It's actually what was required. And the max difference found between experimental and let's say the Particleworks result was actually half of that gap, so 2.8 degrees. So very promising first validation of the method. Let's now move to other sectors, not only automotive. We have food and beverage. Also here we have a very nice example of application of this model for a complex, very complex system that can be tackled thanks to the meshless approach. Here we see actually a coupling. This is a work done in collaboration with Coesia and University of Trento. And all the simulation results are actually results from the master thesis of Matteo Berlato. So you see here a coupling between Particleworks and a multi-body dynamics solver that is Recurdyne, that handles the flexible plastic container that are found more and more in every supermarket, every Aldi, let's say, every Lidl, whatever. So they are new container for soaps or also food, some sort of food. They are more lightweight, but of course, in terms of filling, they introduce complexities because of the flexibility of this system. So what they needed to do was, especially to maximize the filling time, was to simulate the system in a coupled way. So where fluid can impact the shape of the flexible pouch, okay? So only thanks to the coupling between Recurdyne and Particleworks, this could be achieved. So let me just show you a video that shows the entire process, filling process. So you have to imagine a non-Newtonian detergent here. You can see that there is the first stage that is the filling stage. Then detergent is finished filling. Then it's moved. The pouch is moved. You can clearly see the sloshing of the detergent and the effect on the flexible pouch. And then, and this was all done in a simulation in 1 week without very many complexities in terms of handling of boundary conditions. And you can see that also the closing stage is analyzed. Here is another visualization of the flow, especially in the filling with the velocity field. And I think it's very clean and interesting, especially the sloshing part. So, okay, the filling finish. We have the closing of the nozzle, and then we have the sloshing of the detergent with some residues sticking on the walls. And those residues are actually of interest because when dealing with this kind of system, we need to ensure that the closing and the sealing area is not contaminated by the detergent. So that was actually one of the output that was looked at thanks to the simulation. So yeah, in terms of design improvement, as mentioned, the first point was to understand how the pouch configuration, so the container, can impact the forces and the deformation of the pouch itself during the moving stage. Okay, they could test different shapes, initial shapes of the pouch, as well as material rigidity. Okay, and what you see here is basically the deformation of the pouch when we change the configuration at the beginning, so how much the pouch is open, and also the rigidity of the material and the pouch itself. And you can clearly see that they could improve the deformation here, the X misalignment, either working on with a less open pouch initially, A1, or actually, yeah, A1, you can see that it's in yellow and green. Let's say the most important parameter is the shape of the pouch, but then they could further reduce the deformation by increasing the rigidity of the pouch. But I think it's very interesting here because it shows that there are some variables here that plays a role more than others, and with simulation that could quantitatively have an idea of that. Okay, so they prefer to work on the, let's say, initial shape of the pouch, perhaps more than on the material itself. And the other aspects I mentioned is that we need to minimize the sloshing and to guarantee that in the upper region here, we don't have any contamination. So you see here the effect of the sloshing, and of course, we want to maximize the velocity of the filling, but at the same time guarantee that we don't have contamination there. So they could test different machine speeds and also different geometries, as mentioned. And in this case, actually, there was a trade-off found or needed to be found, because as you can see, if we increase the machine speed and if we decrease the filling time or the total processing time, so if we increase the velocity of the packet of the pouch, We have, of course, more sloshing, and we up to, let's say, a certain threshold. But you can see here that with most open pouch, so a slightly different optimized shape of the pouch. So for this case, it was good to have a less open pouch, so a more compact pouch. But for this kind of objective, actually, a configuration where the pouch is more open was found to be better. Okay, so there is a trade-off, because here you can see that it allows this kind of A2 configuration for a faster machine speed. So we can answer question, and if you have any, or if I didn't explain fully everything there, but I would like to move on with also the granular aspects, or the powder aspects that can be integrated in a simulation. As mentioned, we have this module here, Granulworks, that allows for discrete element method integration together with the moving particle simulation. So the idea is that we have the fluid coupled internally in Particleworks with granular or powders. You see here in orange, or let's say, yeah, yellowish, a powder that is mixed by this mixer, and the moving particle part is in blue. We can couple the moving particle simulation solver, but also the internal air solver. What you see here is the finite volume method integrated in Particleworks. I already mentioned that we have several solvers inside there. And you see here the airflow caused by that, let's say, FVM integrated approach. And here you see the powder in a vacuum cleaner type of application. Okay. This one is transport of granular material due to an airflow that enters on the left. And this is a fluidized bed. So at the bottom there, we have some sort of source of air that moves the particles of the solid. So we have a coupled powder air simulation, or actually air plus fluid, non-Newtonian plus powder. So we have different capabilities and possibilities here. I want to mention one industrial example of this approach that was discussed at Particleworks Experience last year, so at our conference last year, by Lorenzo Iorio from Gamma Meccanica. And this application is in the plastic recycling sector. So basically, they wanted to improve the impeller of this, let's say, separator, plastic separator. You have to imagine that on the right here, plastics enters with, so granular material enters with water. And the objective of this system is to separate the water phase at the bottom with the granulate, the plastic granulate towards the top. Here you see the flow visually captured by the post-processing done in Particleworks. You can see the preferential paths of plastic flow. And so this is the first type of output they look at, together with, as mentioned, design improvements. So they could change the geometry very easily of the separator here, of the screw. They could test 3 different designs and see how the granulate at the top could be collected in a faster time or with better efficiency. Okay, so this is the initial rotor, and you can see several designs of the rotor and how the granulate is collected at the top in a faster way, but also how the power usage of the machine can be impacted by the decision and the design of this element. You can clearly see, and this is an output of the software, it lets you predict torque on elements or resistive forces on every elements you have in the simulation, and compute power, resistive power. So you can see the separation efficiency and the total consumption of power. So the green design was actually better suited. So as mentioned, those are some of the validations that I wanted to present in the introduction here. We have other validation in the motor sector, in the piston cooling, in also hydro turbines design, Pelton turbines. And I would like to leave you with also this link, because on our website, you can access all the public material. Part of it was discussed, as mentioned, but there are several other papers that could be of interest to you. So if you scan the QR code, you should be able to access this page, and you see all the sectors where the Particleworks is applied, and you can go through the validations. So maybe now I will take a look at the questions you asked, and then if you have more, we can continue the discussion. I can also discuss in more detail other aspects. So Yogesh asks how we calculate torque and power losses in gearbox, and if we have validated these parameters. So the answer is yeah, the software outputs directly CSV files with torques, churning losses. Okay. In terms of validations, we do have some private validations, but going back to the Carraro presentation at our conference, so this is public material. You can see here, let's say, torque prediction, actually total losses in the gearbox as compared to experiments. So in the first slide here, we see the ISO standard prediction on the churning losses. And this is the contribution together with the bearings churning that is not, let's say, integrated in Particleworks. We only look at gear churning due to oil. So in orange, we have ISO prediction, so tabulated prediction. And in yellow here, you see the results of Particleworks. You can see that the gap, the total gap, decreases between the experimental and the predicted simulated power losses. Okay, so this is an example of how we can improve a workflow, moving towards the experimental phase. Okay, as compared to conventional methods, estimation methods like again ISO standards. I hope Yogesh is. Ahmed asks, can you speak about customer data privacy also UAV sector? I'm not 100% sure what you mean with that. I mean, the results of Particleworks are stored locally, so we don't have any cloud. So every model is built locally and can run locally easily. So with that respect, data is, I mean, we also work with an offline cluster, computational cluster. So that one is not a big concern. Regarding UAV sector or like aerospace, yes, we have applications also there, but not publicly available. So Carlo asked how we managed to couple Particleworks with Recordine, and actually this coupling is, let's say, already present. Like the two softwares are already built to work together. So there is a coupling design by the two software house of the software. So between Prometheus, Particleworks and Recordine are coupled. There is an interface that really helps in the coupling, and it's a pre-built coupling. Okay, so the exchange of information like forces of fluid on the solid, or solid position with respect to the fluid, are transferred during the simulation automatically by the coupling of the two softwares. So the co-simulation here really works in terms of coupled fluid solid. So it's already pre-built, so it's there. Okay, so are there other questions, or would you like to maybe see other validations? I wanted to show also this slide maybe, because I think it's very interesting to see how GPU compute can help in speeding up simulation. So right now, graphic cards, the new version of graphic cards, can compare to, let's say, a cluster of hundreds of CPUs. So this is an important message, because, let's say, up-to-date graphic cards can scale like 500 GPU, just one A100 can scale to 10 times 48 CPUs. And Particleworks also speeds up if we had more GPUs, more compute, up to 4 times when we increase the number of GPUs. You just ask, can you show formulation for power losses in gearbox on splashing? And can you show something, what forces and pressure comes over the... So I think the question is related to how we compute power losses in oil splashing, and forces and pressure, let's say, validations on elements. So, I mean, forces and pressure at the end on the gears at the end are transferred and computed in the torque prediction and churning losses files. So I would say indirectly we validate that with what I showed. Again, on the torque prediction and forces, we do have internal and private benchmarks also for like car sloshing, car wading phenomena. So a car entering some sort of big water flooded area. In that respect, we have pressures on the car and forces on the cars that were validated, but again, it's all internal data, or let's say not published data. For heat exchangers, we did test, and we saw some usage there. It could be, let's say, very beneficial when you have complex geometries of the exchanger, or if you want to have a fast iteration of heat exchanger design. So I would say it's also possible to apply it there. Are there any? Diego asked, I would like to get further information about bigger grain powder simulation. Okay, so I mean, with that respect, when we introduce the granular material, we can input a certain granulometry, and we can also have very big granulate. Okay, so you can see in this example that the powder have different dimensionality. That's one thing we can do. But also here you see that powders can be very big. So no limitation, I would say, there. I also want to mention that if you go to our website and if you go to events, we have introductory days on the software. They are promotional training days. So we give access to a 1-month license, free license, and you can join, let's say, our training and experience and apply Particleworks to any of the system you like. So you can register, and if we have places, we can then help you in let's say, testing Particleworks for your application. So just go to the website, Particleworks Europe, you go to events, or you follow this QR code and you should find the events tab. So Ahmed asks if the particle number can be counted. So if we can monitor the amount of particles, I would say, in certain areas. Yes, we can do that. There are several post-processing tools like probing regions that allows, for instance, to monitor the amount of oil or the number of particles in specific volumes. I would say, if you are also interested in understanding more about the software, you can go to YouTube, Particleworks Europe, our YouTube, and there are some videos showing the interface and how to build from zero a simulation. Okay, so you should be able to find it on YouTube. Omar asks the comparison, the greatest advantages between Particleworks and CFD solution, other CFD solution. As mentioned, whenever we have complex geometries, splashing, jets, oil jets, spraying phenomena, so free surface flow, multi-phase flow, we have a method here that is much easier to set up and to also guarantee that is stable in the solution as compared to traditional CFD. So I would say that one is the main. Luca asks if we can do illumination validation in the automotive regulation. So I'm not sure what you mean there, like lighting system, maybe contaminated by some sort of snow or whatever. that we can do. Okay, but what type of validation? I mean, we don't do the physics of light here, but we could do some sort of coverage of lights due to maybe external contamination like snow. Is the solver, Alexander asks, with only usable with a GUI or also an API? I mean, everything can be automated with a Python proprietary API. So there is also a way to automate every simulation step with Python, and it's yeah, already in place. So no need to open up the GUI. Okay. Diego asks if we can set equation in the program, for instance, variable specific heat or non-Newtonian fluid. Yes, there are several ways to customize both heat transfer coefficient or non-Newtonian fluid laws. We can have user-defined functions there, also in the rotations or in the acceleration profile applied to the system. So the short answer is yes. Yeah. There are also predefined non-Newtonian laws. So let's say, just to give you an overview, we can model snow on a car, and this is a predefined model that comes with Particleworks. But again, for the details, I would say either write an email to us, or reach out on our website, or join the next events, the trial of the software. We have one in 1 week, and we have it monthly. So just go to Particleworks Europe website. You can find all the information. Okay. Alexander asks if we have benchmark test against modern fluid solver like Fluid X3D, Cloud Fluid, etc. No, we don't have publicly available comparison. We have several benchmark, but they were performed by our customer in a private sector, in a private fashion, to compare other mesh or meshless tools in terms of exactly that. And we can say that they appreciated this approach over others. So I can just comment with that. Okay, so that's it on my side for today, I guess. Thank you very much for your interest and attention, and also very good number of questions, very good exchange here at the end. Again, I'm Michele Marelli. I'm part of EngineSoft Particleworks Europe team, and hope we can connect on LinkedIn and maybe also via email, and continue the discussion. So you have the references, you have our website, so reach out if you want to hear more or test the software. Thanks for now, and I wish you a very nice continuation of day.